So this session is about like optimizing Druid at Pinterest. Especially my focus today will be like on real-time use cases at scale. So a little bit about me. So I'm currently a tech lead at the real-time analytics team. I've been working with Druid for like a little over 3 years, mainly to make it more efficient at scale at Pinterest. So first, like let's talk about some background on real-time use cases at Pinterest. When we first migrate to use Druid from HBase, we mainly focus on the batch ingested use case. But as the company grow, and then we want to provide more and more real-time signals to our partners, pinners, and advertisers. So the real-time use cases on Druid at Pinterest mainly power the swift feedback of business metrics to them, like within like minutes of arrival of engagement activities. So here's a classic example that showing, yeah. So basically, if someone like see your ping, then you will basically see the stats updated in a few minutes, which is really cool. And then here are some characteristics of the use cases of real-time use cases at Pinterest. So let's first talk about the scale. Currently, the scale of the largest data source has around 500K to 1 million write QPS. And for read QPS, that's around like 1,000. And the scale keeps growing. And the SLA we provide to our clients is like P99 query latency wise, around like 250 milliseconds. And for the ingestion lag, it's always less than 1 minute. So the goal for our team is to meet the SLA and the scale. And also, meanwhile, we want to be cost efficient because the scale is really large. So we would like to make it as cost saving as possible. So here's a simplified architecture overview. So basically, we have a raw event Kafka where like clients put their like raw events like web logged activities there, and then there's also a Flink ETL job that like do the like cleaning and the processing. And after that, they will put the like the denormalized events into another Kafka topic where Druid will consume from there. So, in terms of the actual setup in the Druid cluster, we know that we have brokers and the middle manager and the historicals, where typically like a scatter-gather architecture. And this is the typical setup for the real-time use cases, where we only care about the most 7 days data. So we have a bunch of brokers, and then we also have a bunch of middle managers at the top that serves most recent 1 hour mutable data. Typically, we use memory-intensive hosts for that to cache all the segments and provide enough RAM. So after that, we also have memory-intensive historicals to serve the most recent 10 hours data. So the reason of the number 10 is because typically for whatever reason, the compaction job can only kick in after 10 hours. So like the most 10 hours data are uncompacted. So we scale them on different server pools independently. And after that, we also have memory-intensive historicals to serve the most recent 4 days compacted data. So the reason for that number 4 is because based on query pattern, most of the queries will hit like most recent 3 days. Like after that, it will hit the ingested data. So we only need to make sure we have enough capacity for the most 4 days. So after that, we also have disk-based historicals, which serves most recent 7 days compacted data. So that's mostly for like a backup. So occasionally there will be batch workflow delay. So like those that stage will be queried as well. But in most of the case, we make sure that the ones in the red box have enough capacity so that we can guarantee the SLA. And since they are all like memory intensive hosts, so they contribute to like more than 90% of the infra cost. So what's the challenges here? So the problem is like, as you can see from the previous slide and the scale, a considerable amount of hosts basically we need to add more middle manager PN task replicas, more historical replicas. Just need to meet the query SLA. You see the QPS is 1000, so it's really high, and also we want the latency to be really low, like 250 milliseconds. If we don't have that many hosts, then we basically cannot get into the SLA. And we also see that the scale is keep increasing. So eventually we found that the infra cost and scale we can support becomes kind of nonlinear. So basically to add like maybe 100 more QPS, we need to add this proportionate amount of hosts. And we try to reduce costs, and by reducing hosts directly, we found that the Druid segments to scan just get queued up and the latency goes up. So basically we cannot reduce any hosts directly. So we brainstormed, and we found the solution to be based on the following rationale. So we have some metrics graphs, right? And the metrics graphs for Druid processing thread usage shows constant heavy usage in production. That means like it's basically a CPU bound problem. And we also know that each Druid segment needs one Druid processing thread to scan. That means there are two ways to optimize. One is we can try reducing the number of segments to scan per query, or we can just reduce CPU usage per segment scan. So next, I'll talk about like the optimizations we have done following these two approaches. First, I'll talk about reduce the first optimization, which is try to reduce the amount of segments to scan per query. So here are the two solutions we found that's useful to achieve this optimization. One is string partitioning. Recall that for batch ingested segments, we generally use hash-based or another range-based, which is another range-based partitioning to group events belonging to the same active entity in the same segment to improve query locality and reduce number of segments to scan per query. Here, the entity usually means some kind of ID or experiment name or advertiser name, like based on the use case that always present in that query. So why don't we do the same on the upstream Kafka producer side? Because there's no like shuffling on the middle manager side. So what we can do is we do it on the upstream Kafka producer side. Another thing we found useful is Bloom filter index. So we know that every query comes with a ping ID to filter on for our use case. So with string partitioning enabled above, during query time, we use hash ping ID more the number of string partitions to determine if a segment needs to be scanned. But you know that the result value partition ID is always a valid integer. So that means like at least one segment will need to be scanned for that particular time bucket for every query. But query pattern analysis shows us that a given ping ID doesn't necessarily always present for every time bucket. So actually, a lot of segments will return empty results if you have, let's say, a query for, let's say, 3 days, maybe only 1 or 2 hours of segments has data for that particular ping ID. But because we use hashed, it will always return a valid partition ID, so we cannot distinguish from there. So this is like wasteful CPU usage, right? So when QPS and time range of the query are high, we basically want to save every single scan. So we need a way to reduce false positives, and the Bloom filter is a good candidate here. So let's go back to the architecture overview and then like see an actual example. So so our focus will be on from the Kafka to Druid side. So here is like the amplified view of the write path of the first optimization. So let's look at an example. So let's say there's a write event with time like t 20 to 3, and then ping ID 123, board ID 456, event type click. So what do we do is we partition by ping ID on the Flink Kafka producer side. So what do we do is we hash the ping ID 123 more the number of Kafka partitions, which is, let's say, 240, and then that gives, for some reason, that gives, for example, a reason. That gives, for example, result, which is 79. So the event will go to partition 79. And on the Druid side, let's say we have 120 PM tasks, and then so basically the 240 Kafka partitions will be distributed evenly to the 120 task PNs. So one task PN will be responsible for two of the partitions. Let's say in this case, partition 79 and partition 199 goes to segment 0. And then on the segment 0's shard spec side, which is basically a metadata of what's in this segment, we see that the interval is like hour 22, and then the partition dimension is ping ID. And then we also record information such as string partition IDs, which in this case is Kafka partition 199 and Kafka partition 79. And we also record the total amount of Kafka partitions here, which is 240. Okay, so this is the segment partition. This is the metadata info for the for segment 0. And let's say after 1 hour, there's a handoff happening. So segment 0 will be like written to S3, and one of the historical will pick that up. So here, there's one more metadata added, which is the Bloom filter for ping ID. In this case, it means in this example, it means Bloom filter ID events with Bloom filter ID 789 and 124 is included in this is included in this segment. Actually, I think there's a typo here. It should be at least like 123 should be included in BF ping ID. I correct that afterwards, but you get the idea. Also, like we can create multiple Bloom filters to help with other queries as well. So in this case, for example, we also add Bloom filter for board ID. So it means here if the event has board ID as 768 or 90, it will be present in segment 0. So so the reason we cannot provide we cannot include the Bloom filter while the segment is in Window Manager is because the segment is still open at that time. It's mutable, so we do not have enough. So we cannot have a mutable Bloom filter in that case because like there's a gap between broker and the middle manager. We cannot like synchronize the real-time updates of the metadata from middle manager to broker, and we don't need to because the string partitioning is good enough at that time. So we wait until the full segment is complete. There's no more new data coming, and then we just create the Bloom filter at that time. Yeah. So once we have that, let's look at the query paths. So let's say there's a query example. Select some CT from data source where ping ID equals 123 and board ID equals 456, and event type equals click, and the time between T20 and the T22. Let's say current time is T22:20, so that means 0, which holds T22 and T23 is still middle manager 0. Segment 1, for some reason, there's late events, so it's also in middle manager. Yeah, so segment 1, and then there's also segment 3 for T20, which is 2 hours ago. So suppose that's already being handed off to historicals, so it has additional Bloom filter index there. For the other two, it only has string metadata. So here's the workflow on broker side. So broker holds all the metadata for all the segments, right? And so to determine the segments needed for this particular query, The first step is we filter based on time. So we make sure that the segment has interval between T20 and the T22 based on query. The step 2 is filter on string partitions. Make sure that the recorded partition ID's metadata contains what the query is looking for. And then the step 3 is we filter based on Bloom filter if available. Make sure that at least the Bloom filter has the ping ID or board ID. So the conclusion is we scan this segment if all steps return true. So let's look at the first segment aspect. So step 1 is true, like the time range matches. Step 2, so basically we are looking for a segment that has string partitions ID 79, and then this matches. So step 2 is true. So step 3, this is not like there's no Bloom filter available, so we treat that as true. So the conclusion is true. So we will scan this segment. For segment 1, step 1 is 0. The time range matches. For step 2, it's false because the string partition IDs it contains 18880 doesn't match 79. So we bypass this at this time. For segment 3, step 1 is correct because the time ranges matches. For step 2, it also matches because the string partition ID it contains has 79. For step 3, it's false because we need to make sure there's a ping ID 123. But for the Bloom filter here for ping ID, it only contains like two other ping IDs. So we bypass this. So the conclusion is false. So broker will only send the request to segment 1 to middle manager 0. So we can see that with only step 1, which is by default for Druid, right? All 3 segments matches. So like there will be 3 requests sent out to 3 hosts, and with step 1 and step 2. So basically one additional one improvement there. Then 2 segments will match. So we will scan 2 segments. But with step 1, 2, and 3, only 1 segment matches. So the false positive rate is at the minimal. So only 1 segment matches. So you can see this helps to reduce the number of segments to scan. So here's our result. With optimization 1, we found that in production, a considerable amount of segments can be pruned on the broker side. So here's a summary, like for P99. So without partitioning, there's 0 pruning that can be done. All segments need to be scanned. With partitioning on the string side, we see that about 44% of the segments can be pruned on the broker side. But with both string partitioning and Bloom filter, we see that for P50 requests, like close to 90% of the segments can be skipped. So that saves a lot of bandwidth on the bandwidth and load on the historical side. And also here's a thread usage, processing thread usage of the historicals. We see that after this change, historicals experience way less load. So we also able to shrink the cluster to use less amount of historicals to support the same SLA and the scale. To enable the optimization 1, we also made it very simple. So for string partitioning, we can just specify in the Kafka's indexing supervisor spec as one of the contexts, just partition by ping ID. Also, we also have a variant on that. If we think that for this use case, the dimension value has a potential skewness. For example, some advertiser has more data than others. We can also have another parameter, partition fan out size, to when we hash the data to different partitions, we make sure that it actually goes to 3 partitions instead of just 1 to help with the skewness. And for Bloom filter, it's also easier to enable just like 1 more parameters on the dimension spec for whatever amount of dimensions you want to enable. Yeah, let's talk about optimization 2. We can also try reduce CPU usage per segment scan to make it more efficient each scan. So So here we are talking about, we will first talk about segments in middle managers. So here's the rationale. So we have metrics showing latency is linear to the number of rows in memory. So on the left bottom side, this is the typical graph for number of rows in memory before that segment persists to persists to disk. So it's like a zigzag shape, and we found that the latency is quite similar to this shape. So that means like it's kind of linear to the number of rows in memory, right? So we look into the storage format as well, which shows rows are stored in a giant map without inverting index when in memory. So that means like there's no index, right? So all rows needs to be scanned for any given query. That's kind of like an all-in operation. But we recall that batch ingested segments has bitmap index. So why can't we do the same for real-time segments as well to make the query all one? So on the right side, there's another example. So before the change, for every query, let's say there's currently 1 million rows in memory. That means in order to filter on, let's say the query contains a filter on like where ping ID equals 1, 2, 3, we cannot directly pinpoint rows 0 and row 2. We need to scan every single 1 million rows to finalize before we can decide that only rows 0 and row 2 matches. But with this optimization, we can look into the index and then directly pinpoint row 0 and row 2. For most of the case, like that's the typical case because what the query actually looks for can be pinpointed to only a small amount of rows instead of the 4 rows. So that also can be verified from the production request analysis. That's segments in middle managers. So what about segments in historicals? So we know that middle manager tasks are responsible for like 1 or 2 hours of segments, while historicals are responsible for like 24 hours or like 3 days in our case for the real-time use cases. And with the same high read QPS, we want to make sure that historicals is as efficient as possible as well. So we also know that the use case is CPU bound because of high QPS. So in general, we have provisioned the clusters in such a way that we have redundancy. We have CPU shortage, but we have redundant RAM. So we have enough RAM to cache all the segments in memory. So I/O is really fast. So we can actually trade some I/O for less CPU. So what we do is we disable dimension and metric compression for segments on the historical side, just to make the segments larger, but we still have enough RAM to cache them to make it less CPU intensive. So the result is with the in-memory bitmap and the disabling of compressions in the persistent segments, we see that the latencies are greatly improved. This is one of the greatest graphs. So we see that previously it took like 30 seconds for the same amount of QPS. Right now it's like hundreds milliseconds. So it's greatly improved. And also previously like one middle manager can only host one PN task because like for a 32 core machine, because the scanning is really inefficient per scan. So like 32 cores is already like so one PN task with street processing thread 32 is kind of like using up all the 32 cores. So we cannot like put more than one PN task on one 32 core machine. But with this change, we suddenly now have redundant CPUs compared with before. So we are able to put more than one PN tasks on one 32 core just to let it share. So in this case, we are able to put like 12 PN tasks on there. So that means we are able to use less hosts as well to support the same SLA and the scale while saving some cost. To enable optimization too, it's also really like convenient. We've made it really easier to use for our clients. So basically, we have a flag enable in-memory bitmap in the tuning config of the Kafka indexing supervising spec. We just set it to true. And then for disable compression, that's already included in the Druid release, so it's not added by us. So you just like set uncompressed for metric and dimension compression for the final index spec when you actually create the final segments that will need to be handed over to historicals. Yeah, so that's basically it. So let's also talk about the metrics to tune real-time use cases that we use. I'll leave out like QPS and latency, assuming that everybody will use that. So for monitoring, one metric we found really useful is the Druid processing thread usage. This is basically shows whether the cluster has enough CPU. And if you see that, so in this case, in this example, it seems fine because like it's not very packed. And also like the maximum 32 is not like constantly hit. So probably we are in a good shape. And also it has another one called like merge buffer usage. So a lot of the queries are grouped by queries, and we want to make sure that those queries are not blocked due to shortage of buffers. So here you see that the maximum we allocated is 25, but like constantly it's not like it has sufficient amount of merge buffers. It's not like hitting 0 all the time. So we probably also good that in this case. And also like for ingestion lag, we basically use two metrics. One is the time. Basically we have a timestamp on the Kafka event, and also when we ingest them, we compare with the current time. So that means like we can see the gap between when the event is added to the topic and when it's processed by Druid. So here we see that in this example, it's mostly below like 30 seconds, which is 1 minute, which is good. So we are good. And also there's a Kafka offset base. So we just deduct the calculate what's the current front in the topic and what's the current offset of the record we are processing and deduct it to get a sense of whether we are lacking too much. So basically there are two dimensions of showing whether we have ingestion lag. So here's another one. So this is the number of rows in memory. So this is what we use to provide optimization to. So it is basically used to tell if persistencies for some reason unnecessarily trigger too often due to the time-based triggering threshold that you set, or because of there are late events. So it persists like very often. So in this case, it seems good. It doesn't persist until it reaches 1 million. So that's expected. Also here is the metric of number of segments to scan for each query before and after pruning. So this is used to tune optimization 1. We see that before the segment pruning, it has something like 8,000. And then after the segment pruning, it only needs to scan, let's say, 3,000. So we know that there's kind of 60% reduction. Yeah. So with all the good things, we also talk about like the current pain points in real-time use cases that we are planning to address and or work with the community to address next year. So one thing is overall scalability. So we found that many pieces in workload is kind of like single-threaded and not able to keep up with serving the metadata requests. So the amount of metadata requests it's required to serve is usually proportional to number of data sources times number of tasks, times replicas, times active time buckets. If you have like scattered related timestamps, like there will be multiple time buckets or like segments open. So we really want to improve that part, which I think currently is the bottleneck of serving higher scale use cases. Another thing we found inefficient on the current Druid side is real-time ingestion. The way it like distribute the string partitions. Currently, if one string partition has delay, the whole data source is delayed because only a single consumer is assigned to work on a given string partition. So if that partition has problem, you cannot distribute the load. So kind of like a tail lag. Another thing is we also see there should be room for improvement on the continuous compaction side. We know that compaction is a major contribution on efficiency. So if we have a lot of late events, then there will be a lot of small segments, and whether we can compact them in time is really important. So there are existing Druid minor compaction, which is supposed to solve this continuous compaction problem while the normal ingestion is ongoing without like holding logs on each other. But I think currently it's not full-fledged enough to compact completely contention-free. Or another thing we found is just currently it seems the minor compaction doesn't have enough parallelism to completely replace the major compaction. So we are really looking forward to solve that. So on the query side, one thing we found that is for the aggregation limit parallelism, we all know that currently there's only like 2 layers of aggregation. We basically have enough, we basically have infinite number of leaves, where leaves means data nodes, which is middle managers and historicals, but we only have a single root. Like even if the broker can be multi-threaded, but that's also, but that's eventually a single node, right? So we found that many tail latencies can be potentially improved if we can have like one or more additional layer of intermediate aggregation layer between root and leaves, so that the aggregation power can be improved. Another pinpoint we found is we found that Druid has like limited index types compared with other like OLAP solutions. So like currently the amount of index types are very limited. So we have primary index, right, which is time that broker can use, and also like secondary index, which is hash of key or range of key based on the partitioning mechanism you use. And this is also used by the broker. And finally, on the historical side, we have individual column-wise bitmap index. But we found that in production, like the query performance has kind of noticeable degradation if we have increased number of filters. I think it would be beneficial to have more index types, just to name a few, like sparse index, zone map index, bloom filter index, and star tree index, etc. I think that will help us like having a like faster like query performance for sure for other for more like complex use cases. Yeah, that's basically it. Like if you have questions, feel free to reach out to me or our team. And also, we also have a blog post that has some more details on the learnings. Feel free to check that out. Yeah, thank you. And feel free to contact our team or me directly. Yeah, I can take questions.
Definitely. Thank you, John. This is a great session. There's lots of questions here. Let me help you out there. Just one question. When partitioning by pin ID, is there a concern that a particular pin may create a large number of events and cause data skew on the Kafka partitions or in the Druid segments?
Oh yeah, that's a great question. So so basically on the data architecture of like Pinterest, we have like advertisers, campaign, ad group, pin ID, board ID. I think pin ID is the lowest granularity. So usually we don't have a lot of skewities on that. But in case your use case has the skewness on that side, we also, so there are also use cases where we partition by advertiser ID. So in this case, if you look at the left button, we also have a solution that when we hash, we actually hash it to like 3 partitions instead of 1. So fan out, so partition fan out size is a tunable parameter, which will control like how many target partitions your ID will potentially be hashed to. So like given a fixed advertiser ID 123, the likelihood of it to be sent to like any of the 5 partitions is the same. So there are some randomness there, but that helps with the skewness. Yeah.
Got it. One follow-up question, if I may. The additional context parameters that I see here, is this something that Pinterest built on top of Druid to manage the ingestion?
Which one?
The partition in the screen, the partition dimensions and the
Yes.
partition fan out size.
This is customly built by us. So we are trying to open source that as well in this year.
Thank you. All right. The next question is about the Bloom filter. Is the Bloom filter created during real-time ingestion or in a separate process afterward?
So it's created when the PN task finishes the ingestion, and then basically merge and combine the existing intermediate segments and upload to S3 for historicals to pick up. So it's so the short answer is it's created when it zips all the intermediate segments and upload to S3. So it's yeah. Hope that answers your question.
Got it. Thank you. And same with the Bloom filter. Does the query user need to add a Bloom filter clause manually, or is it added for the user by a middle layer?
You mean like how to enable the Bloom filter?
I think the question is more about when the query is coming in,
yeah.
How do we let the query know to use the Bloom filter? Does the query, who are writing the query, do they have to say to use the Bloom filter, or is it automatically used?
Oh, it's automatically used. So if you look at the example here, so each segment has like a shard spec, right? So so here it's a string hashed, and then so when the broker verifies whether the segment needs to be scanned, it also takes into account the corresponding Bloom filter associated with this segment. So it just checks whether the existing entries in the Bloom filter, in this case like ping ID and board ID, matches one of the query filter. If the query contains filter on ping ID, it checks whether the available Bloom filter for this segment contains the entry like ping ID 123. So it's so in short, that's automatic.
Thank you. All right, there's another question about compression. How much data size increased by disabling compression?
I think that's a lot. At least probably like 2 times or like 5 times more. But I think, yeah.
Thank you. 2 to 5 times more. Okay. All right. There's another question around the latency. Do you have a graph on historical latency improvement with compression turned off? The graph you have showed both middle manager indexes and historical compression off. I see how middle manager indexing improves greatly. Do you have metrics for historical?
I think I didn't include it here. So let's get that. So yeah. So yeah, I don't think I include a separate one here. I think I can get a separate one. Maybe like you can email me so that later I can send to you.
Got it. Definitely, yeah. Thank you. All right. There's another question around the monitoring as well. Where all the charts in the monitoring section built from native Druid metrics? Did it require custom instrumentation on your side?
Yeah, so basically we added some missing metrics to the Druid code base. I think that's also like pull requests for that for sure. So basically, I think once the pull request is merged or you use that pull request, then I think they're automatically there. So these are all like emitted from Druid. We don't use like any custom build.
Got it. So there are custom metrics, but however, you use the base Druid metrics framework to emit your custom metrics. Is that correct?
Yes. So yeah, so basically we just modify Druid code base to emit some of the metrics that we think are useful, but currently are not there.
Thank you. Thank you very much. There's a question around the compaction. Do you run compaction tasks that will recompress the segments for the longer retention segments, or keep all uncompressed?
In general, we compact every time because I don't think there's a case we don't compact. We basically compact every time, just to so on the batch compaction side, we also have some custom like basically like after compaction, the segment format is more efficient in the sense that we also have some logic to treat like skewed data. We to reshuffle the skewed data during the major compaction side to make it more efficient. So the short answer is we compact every single time if we can.
Thank you. Thank you very much. There's another question on the session tab. When selecting stream partitions, is high cardinality of the column an advantage?
I think for our case, I think that the ideal candidate will be a column that you will always use in your query. So basically, if that column is always used as a filter in your query, that will be an ideal candidate because you not only want the data to be like scattered during ingestion time to be evenly. You also want to like use that knowledge while you query to prune the segments based on that. So if you do not use that if you do not use that dimension on the query side, then still all the segments needs to be scanned. Maybe like underlying like one segment can be processed more efficiently with the partitioning, so that because the data has more locality, but still all the segments need to be scanned if we cannot distinguish whether we need to scan a particular segment because you don't have that dimension on the query used. Hope that makes sense.
Very nice. Yeah, that definitely makes sense. All right. So we are coming to the end. I think we might have time for one more question. Let me go back here. Is there any ideal segment size that you found optimal in historicals?
Yeah, so I think in general, like the amount of rows has more impact. So we, in general, like use 5 million rows per segment. But it also depends on your query pattern, right? So you know that like only one thread can scan a single segment at a time. So sometimes if the query pattern needs to scan like all the 500 million rows in a segment, so that means potentially that is too slow. So for that, so we have some use cases where, let's say, one advertiser has billions of rows. So if we put like all the 500 million rows for that advertiser in one segment, it's too slow. So on the major compaction side, we have a custom partitioner to like move one large partner's data across all the segments, so that there's more parallelisms there. But I think in the general case, like 5 million rows per segment is what we use.
Very nice. This is a great session, John. I really learned a lot today, and thank you for all the attendees as well.